there are whispers in the world of aviation. They speak of a shadow that moves faster than any aircraft known to man. It is a myth. It is a rumor. It is a ghost in the high atmosphere. They call it the SR-72, more evocatively, the Darkstar. This is not just a story, it is a possibility, born from the minds at Lockheed Martin's Skunk works, the very same innovators who gave us the legendary SR-71 Blackbird. The tale begins where the Blackbird's story ended, a legacy of untouchable speed. But the Darkstar is said to be something else entirely, a machine rumored to reach speeds exceeding Mach 6, a velocity that borders on the fantastical and redefines air-breathing flight. The SR-72 represents more than just a successor. It is a leap into a new domain of flight. It exists between confirmed fact and speculative fiction, teased through cryptic statements and conceptual art. The SR-71 Blackbird was the undisputed king of speed, a marvel that could outrun missiles. The central promise of the SR-72 is its astonishing velocity. The design goal is a sustained cruising speed in excess of Mach 6. To put that into perspective, this is more than 4,000 miles per hour, or well over a mile every single second. At such speeds, the aircraft could traverse the entire continental United States in under an hour. This is not simply an incremental improvement over its predecessor, it is a fundamental paradigm shift. The SR-71 Blackbird, a titan of its era, topped out at a little over Mach 3. The SR-72, therefore, is being designed to operate in a flight regime that is twice as fast, presenting engineering challenges that are exponentially more difficult to overcome. The airframe must be designed to withstand immense friction and pressure. This quest for Mach 6 dictates every aspect of the aircraft's hypothesized design. It would almost certainly feature a highly blended wing-body shape, where the fuselage and wings form a single, seamless, and incredibly strong structure. This is not just for aerodynamic efficiency, it is a necessity for managing the colossal forces and extreme temperatures encountered at hypersonic speeds. The surfaces would need to be perfectly smooth, with knife-like leading edges to slice through the air with minimal resistance. A delicate balance between two vastly different worlds of aerodynamics. The most profound innovation rumored for the SR-72 is its propulsion system. To achieve the dream of Mach 6, a single type of engine is simply not enough. The solution is believed to be a turbine-based combined cycle, or TBCC engine. This is essentially two engines fused into one, a brilliant but mind-bogglingly complex concept. The first part is a conventional turbojet engine, like one on a modern fighter jet. This engine gets the aircraft off the runway, climbing to high altitude, accelerating to around Mach 3. It compresses air with spinning blades before ignition. At the turbojet's limits, the TBCC's magic must happen. The turbojet would shut down or be bypassed, and the scramjet takes over. A scramjet has no moving parts and uses forward velocity to compress air. Air rushes in supersonically, mixes with fuel, and combusts to create thrust. The mode transition must be seamless, stable, and reliable. Imagine trying to light a match in a hurricane. That is the scramjet challenge. Engineers shape the flow to keep flame holding without shock-induced flameout. Crack TBCC, and a runway to hypersonic aircraft becomes practical and reusable. Section 4, Eyes and Talons, the missions of a hypersonic ghost. The primary role envisioned is a direct evolution of its famous ancestor, Intelligence Surveillance Reconnaissance, or ISR. In a world of rapidly shifting threats, speed of information is paramount. A hypersonic platform could overfly a developing crisis, a military buildup, or a suspected weapons site, delivering real-time imagery and signals within minutes, not hours. Its sheer speed covers vast territory in a single sortie, mapping positions while remaining nearly untouchable. Beyond reconnaissance, the SR-72 is discussed as a potential strike platform, transforming from observer to participant. Armed with advanced compact munitions, it could perform deep strikes against time-sensitive, high-value targets. Launch from thousands of miles away and arrive before the window closes. Flexibility comes from unmanned or optionally piloted variants. Unmanned removes risk to pilots and human limits on G and endurance. Optionally piloted, retains human judgment for complex missions. Is it watching or about to strike? That uncertainty is its psychological edge. Section 5, a cloak of heat and shadow, the paradox of hypersonic stealth. Achieving stealth at Mach 6 presents a profound contradiction. Traditional stealth like the F-22 Raptor and B-2 Spirit use shape and radar-absorbent materials to deflect or absorb radar, making them appear as small as a bird, or even disappear. SR-72 would feature sleek, angular tailless shaping with aligned edges. The goal, approach without setting off alarms. But hypersonic friction heats the skin to extremes, creating a massive infrared signature, a beacon to heat-seeking sensors. Shockwaves and ionized air add detectable cues, near invisible to radar, obvious to other sensors. Solutions may include circulating fuel as a heat sink, new low-emissivity materials, and shaping to cool the thermal wake. The doctrine is delay, not vanish, shrink detect to engage to near zero. By the time it is seen, the Darkstar may already be gone. Section 6. The Silicon Mind. Avionics and autonomy at the edge of control. At over a mile per second, avionics must be revolutionary. A silicon mind processes and decides faster than any human pilot. Flight controls make thousands of micro-adjustments each second to stabilize in thin, turbulent air. Systems must be hardened against heat, vibration, and electromagnetic interference, a hostile environment for conventional hardware. AI is central, especially for an unmanned SR-72. It can handle engine mode transitions and evasive maneuvers at Mach 6. AI triages vast sensor streams, identifies targets, flags threats, and manages ECM. Sensors must see through a superheated plasma sheath that can distort comms. A multispectral suite, optical, infrared, and advanced radar, feeds 360-degree awareness. Integrated avionics and AI turn a fast jet into a networked entity. It coordinates with satellites, other aircraft, and ground stations, sharing data across a battle network. AI-assisted targeting expands capability and raises ethical questions. SR-72 is as much computation and autonomy as aerodynamics and propulsion, a future where the pilot may be in the code. A silicon co-pilot at hypersonic edge speeds. Section 7, Veils of Secrecy, Hurdles of Physics, the Uncertain Path Forward. Despite compelling logic and tantalizing hints, the SR-72 Darkstar remains officially unconfirmed. Its existence is wrapped in layers of classification and deliberate ambiguity. Lockheed Martin, the US Air Force, offer careful words and concept images, but no formal program announcement. Secrecy is strategic. It keeps adversaries guessing and blocks countermeasures. The public is confused. Analysts sift signal from disinformation and speculation. Beyond secrecy lie immense technical hurdles. Hypersonic physics are unforgiving. Managing heat demands breakthroughs in materials. TBCC must prove reliable across vast speeds and altitudes. Every component, from fuel pumps to actuators, must survive extremes. Entry by 2030 is rumored, but such timelines are often optimistic. Budgets, setbacks, and shifting priorities can slow progress. Each test pushes into the unknown and feeds the next iteration: design, build, test, learn. The path to operational hypersonic flight is long and uncertain. Yet the SR-72 matters as national ambition. Engines, materials, AI will advance regardless. For now a ghost, casting a long shadow, our next great leap is just over the horizon.